Hello everyone, we are ALLURT Engineering. I want to introduce the team today. My name is Rylan Larati.
My name is Saleh Griswold.
My name is Logan Heck.
My name is Anthony Hasso.
My name is Luke Otten.
And today we'll be going over our design and integration of the chip and chunk tire testing trailer for Continental Tire and Uvalde Proving Grounds. This project was presented by Continental Proving Grounds in Uvalde. They were presented to the UTSA College of Engineering. Their goal with this project was to have a young team of engineers work and design a trailer that would allow them to better test their chip and chunk tire testing methods. So what the Continental Proving Grounds are, it's a big testing facility out in Uvalde. They have a few paved surfaces and a bunch of off-road surfaces where they test a multitude of different tires, different tire sizes, different tire types. And so what they wanted with this project was a specific trailer designed for one particular test, their chip and chunk testing system, And this trailer would allow the Continental Proving Grounds to more efficiently test a multitude of tires by only utilizing one driver. That would cut down tremendously on cost. It would also allow the team out there to get better test results with a more controlled environment. So our team, ALLURT Engineering, has taken all their design specifications and design requirements into consideration, and we have now come up with this trailer design.
So here's our design concept for the trailer. What it is, it's essentially a bed trailer with a single axle running down through it, and on the back of it are attachments for two caster tires, as we say. They're essentially smaller trailers that run on the back and have positions where they can be loaded, and they have single tires on them. And you can supply 2 to 3 of these casters on the back of this trailer. We designed this trailer using many design specifications given to us by Continental. 3 of them primarily were: first specification, the trailer can only be so wide. We were given a 13-foot width for this total trailer, such that driving the trailer would not throw valuable gravel off of their courses from being too long. A second design specification was that every single tire positioned on this trailer had to run in their own direct path, such that no tires could be in line with one another. The third specification was that every tire had to be able to line up with the Continental's scaling room. They have a room at the proving grounds, which is essentially large scales planted on the floor so vehicles can run over them and be weighed. And every tire on here needed to be designed or positioned such that they could accommodate their already existing scale house. So what our trailer is used for is chip and chunk tire testing at the Uvalde Proving Grounds. And the way those tests are run is by applying a load to each individual tire of a maximum of 2,300 pounds to simulate a sprung weight of a real vehicle driving on these tires. And these tires are run on rough aggregate courses and off-road courses so as to get an estimate of how much these tires have chips and chunks flying off of them. So what our goal was with this trailer is to put as many tires on one single trailer as possible. But with the specifications listed earlier, it became almost a very hard task to be able to expand more and more tires with the given width and we had. So we came up with a design to have 2 sidecar tires running along similar to these caster wheels. But after reviewing, Continental said that these tires, a sidecar design would not be doable. So we did away with them, and now what we have is a 4-wheel trailer, which is just 2 casters in the back, but it can accommodate a 3rd caster. So here's a closer look at our caster design. It is not finished yet, but what we are thinking is having a basket system to load weights onto it and an independent suspension on the bottom of it. What it has here is a pivoting arm to accommodate different tire sizes, and with different tire sizes require different bolt patterns. So we still are yet to come up with a design to accommodate an independent suspension on these smaller caster wheel trailers with different tire sizes and different bolt patterns. So because of this design specification that every single tire on this has to be offset and drive over its own independent path, that made our design, it made that design specification became very complicated for our current design. So we pitched an idea to Continental of positioning a grading system on the back and front of a trailer. And essentially what it does is it runs along with the trailers, daisy chained to them, in order to regrade and retender the gravel on the off-road courses, so as to essentially make it so every single tire can go over its own virgin territory, even if a previous tire has run over it before. And what can be done is we can attach we can have the truck with a gravel grading system behind it to accommodate the truck tires running over the gravel. And then behind that, we can have the trailer system. And behind that, we can have another gravel system. And behind that, we can have yet another trailer to accommodate the most amount of tires available per one vehicle driving.
The next part of our poster is the Gantt chart, which shows the amount of work done for each of our major deliverables throughout the semester. The major deliverables include forming the teams, getting project approval from the clients and our professors, the specifications and standards document, the engineering analysis, the poster itself, and then finally the drawing portfolio, which will be turned in later this semester. Keep in mind that this is a shortened version of the Gantt chart in order to fit the poster. The full chart is available upon request to anybody. The chart will show you that we were behind on two major deliverables throughout the semester. The first being the specifications and standards document, which we finished about a week late, kind of because we got our project a week later than most other teams during the fourth week. And then the next deliverable was the engineering analysis, which we started late, and so sadly we finished rather late as well. The next part of the poster is the earned value management plot, which shows the amount of labor, cost of labor that each of our team members put in this semester put together. So the budgeted cost work performed shown here is below the budgeted cost of work scheduled. This shows that throughout the semester we were fairly behind at certain parts. Each vertical dashed line shows a major deliverable, and it's at around the 10th week where we also start to get a little over budget. Throughout the semester, we managed to remain relatively under budget, as you can see by the actual cost of work performed being under the budgeted cost. But it was around the engineering analysis right here shown by the black dashed line, where the amount of work our team put into the project started to increase dramatically. And because of that, in the past few weeks, we have been a little over budget. As for the manufacturing cost of the trailer, Continental Tires in Uvalde has promised to provide the budget for the materials, the machine parts. This right here, this table is a cost breakdown of the cost it'll take for the entire project. We find it very likely, though, that the materials and machine parts might end up being more as we go into Senior Design 2. What's shown here is more a minimum estimate. It's very possible, though we'll try to avoid it, it's very possible that these costs could increase as we go into Senior Design 2.
My name is Tyler Griswold. I did the engineering analysis for the project. The engineering analysis I did in conjunction with my finite element analysis class. For that class, we have a final project over the span of 6 weeks where I do engineering analysis on the trailer at critical locations on both the main trailer assembly and the caster assembly. For the poster, this was the first project update that I did. For this analysis, I did the analysis in Abacus CAE. That's a finite element method computer-aided engineering software that's able to analyze the structure of the beam under a certain load, and then calculate the stresses and deflections that occur as a result of that load. The results of that analysis were that the stress locations located on the end of the beam, as you can see right here and right here, were due to a deflection that was caused from the point load applied to the beam. The goals of the analysis were to analyze the effects of shrinking the profile size of the beam to reduce the cost of the material and the weight of the beam. And the first iteration of the design was a 12-foot long trailer with a 12-foot long I-beam. This analysis looked over what were the effects of when we reduced that beam length from a size of 12 feet to a size of 6 feet. It looked at the sizes of 12, 8, and 6 feet. And then it looked at the profile sizes ranging from 12 inches in height by 31.8 pounds per foot to 3 inches in height and 5.7 pounds per foot. The results of the analysis were none of the stresses or deflections recorded in the analysis ever came close to the actual yielding stress, which was 36 KSI. So to analyze what were the effects, the recorded stresses from the loads of all the different lengths and profile sizes were then compared to the yielding stress, and they were rated on based on the relative closeness to the actual yield. The conclusion of the analysis was that the optimal beam size was 8 inches by 18.4 pounds per foot. This was decided because the benefits of reducing the weight and decreasing the cost of material decreased as the beam profile decreased. So for the structural integrity of the frame, it was better to stick with the 18.4 pounds per foot compared to 5.7 pounds per foot, which was the smallest beam profile. The material chosen for the analysis was A36 steel. A36 steel was chosen because of how the I-beam is connected to the frame. The I-beam is connected to an 8-inch C-channel perimeter, and it's welded. The two material choices in I-beams were A36 steel and aluminum. Aluminum was not chosen because of the problems of welding aluminum. Because of the high thermal conductivity, it takes higher wattage welding, and the high thermal coefficient causes distortions in the weld that produce stresses in the weld and ruin the structural integrity of the frame. So A36 steel was chosen. This was the first project update that was done. Over the 6 weeks of the project, more analysis will be done, but that's it.
Hello, my name is Anthony Hasso. I'm part of ALLURT Engineering, part of the UTSA Mechanical Engineering. So today I'm introducing the conclusion of our findings with the multi-axle tire tester trailer. Ultimately, the tire tester trailer will minimize the labor costs and maximize the tire testing efficiency of the procedure in tire testing that goes on in Continental Tire. So in Continental Tire's proving grounds, they do a chip and chunk multi-axle test that drags along tires along a road with gravel. So our mission was to minimize the labor, maximize the efficiency of the test, and our group came up with the design to add 2 caster designs with baskets that have individual loads for consistent testing. Okay, ALLURT Engineering has also came up with a grader system. We discussed it with Continental and our professor, Dr. Axler, and we decided that a grader system will help with the repeatability of this test by adding another trailer behind it if we have a grader in between. The grader will even out the gravel while testing to make for consistent tire testing. Initially, the project was so we can do a minimum of 4 sets of tires. So that was our initial scope of the project. After talking to Continental and our professor, we decided to move the grader system to another senior design 1 team in this upcoming semester, which instead of it being a 9-month period of performance, it would move to a 13-month period of performance, which would increase the schedule but still work with the scope of the project. So while working with the schedule, keeping with the scope of the project, we decided that this design will maximize the tire testing efficiency and minimize the labor costs. So with that, we just want to say thank you to UTSA Engineering, Class College of Engineering and Integrated Design, our professor, Dr. Axler,